Hello, Darlington. Very nice to meet you online. Thank you for accepting the invitation to come to our TRC conferences. We are very much looking forward to hearing something from you. So this is kind of an interview. So please feel free to share your experience with us.
Well, first of all, I'd like to say I really appreciate being invited to appear at the next conference after the last one, after a 4-year hiatus. And it is a great pleasure to meet with you again. I'm looking forward to being able to share some ideas with you in this coming interview.
Okay, great. Thank you, Darlington. Actually, we are very interested in your over 50 years teaching research and services to the pavement engineering. We all know that you recently officially retired from Texas A&M University. Actually, we want to learn from you that what did we do right and what did we do wrong in the past 50 years in the pavement engineering research community. What do you think?
Well, looking back over 50 years, I've known a lot of the people who actually worked on the experiment, the big field experiment of the Asheville road test back in the 1950s. I worked with them, I knew them and wrote papers with them and so on and so forth. And it's kind of amazing to me that I can look back over that long span of time, which is certainly over 50 years, and give a candid opinion of what we have done right and what we have done wrong. But frankly, I think that every step of the way, we were trying to do the right thing. Looking back on it, I don't think we could have done a whole lot different than what we had. And we would have done differently if we had had the right tools. Back then in the 50s and the 60s, we wanted to do a lot of things, but the tools, the mechanics, the computers, they just were not adequate to deal with pavements, adequate as they are today. Much of the predictions that we've made of the effects of traffic and the environmental and climatic stresses were very approximate. They were the best we could do at the time, but they were really not adequate to deal with a complicated structure like pavements happen to be. So we made maximum use of regression analysis on the distress that was observed. And a lot of times we had to wait for the distress to show up before we could make any of these kinds of predictions. And the reason for predictions is very simply this, that we need to be able to anticipate when the distress at a critical level develops. The when is important to management. And if you miss that timing, if it happens faster than you thought, it's going to throw a lot of pavements into a backlog, and it will make the distress, which keeps getting worse all the time, even worse and more expensive. So this is not a trivial idea. We were doing the best we could, but the tools that we had available to us were just simply inadequate. So what we did right was to stay focused on what the real problems were, the actual long-term management of a pavement network. We knew that we needed to be much more precise in our estimates of how long these pavements would last, and much more, we needed to have much better understanding of the mechanisms by which these pavements would be distressed and would be damaged. So as our tools improved, we were able to improve our predictions. We started out with equations and predictions that were almost purely empirical. In the 90s, we began to transition into mechanistic empirical, in which there was a hybrid combination of these two. Now, finally, after all these years, our understanding of the mechanics of pavements is at such a place where we should be thinking of going entirely mechanistic.
Yeah, Darlington.
It was not that we rejected the use of mechanics back then. It's just that we didn't have them. And we've learned a lot in the last 50 years, and we need to start applying it.
Yeah, thank you, Darlington. We all agree that mechanics is becoming more and more important in the accurate performance prediction for the pavement structures. However, as you know, the intelligent technologies, such as the artificial intelligence, those new technologies are available. What do you think? What role will mechanics play when such intelligent technology become more and more popular? How will make full use of mechanics in the future pavement performance predictions?
Well, our mechanics are able to do much more than just simply calculate stress and strain. We actually can calculate the crossing of thresholds where cracks begin to grow, and also when cracks get so large that they cannot be healed. We can predict healing, we can predict aging, we can predict plastic deformation. We can predict a lot of these things that actually occur. Of course, back in the 50s, we didn't have any of this ability, but we need to use all of that ability, and mechanics can deal with each and every one of these things so that we can anticipate practically at the time of construction how long a given pavement will last. Of course, the things that we don't know for sure, like the amount of traffic and the kind of weather that's going to occur, can also be taken into account. But it's absolutely necessary for good management of a network of pavements that the appearance of distress and the rate at which it increases with time can be predicted. The reason that it's important is because repairing, maintaining, or rehabilitating a pavement at exactly the right time will increase the useful life of the pavement and cut way down on the cost it takes to maintain the entire network. And it's the cost that we have, unfortunately, because of the way that we have had to build up our knowledge of pavements, we now have a huge backlog, and the amount of money available to repair and rehabilitate pavements is just far more than we can catch up with in just a year. It's going to take a number of years, maybe decades, for us to actually catch up and get on top of our pavement deterioration problems. So mechanics is going to be right there at the center of it. And the two things that need to be emphasized are that we need to be able to not only predict stresses and strains, but the actual distress itself in terms of the things that can be measured, the cracks, the crack lengths, or the total volume taken up by micro cracks, and running the actual shape and displacement that occurs. All of these things can be done, and we need to move in that direction rather than using subjective scales like we've had to use in the past.
Yeah, yeah. Thank you, Darlington.
On top of that, we need to make much greater use of non-destructive evaluation, and I'm sure that radar will play a much more important role in the future, although it's not going to be the only one.
Yeah, Darlington,
we must use in the future.
Yeah, actually, that's my next question. What do you think in terms of where the pavement engineering will go in the next 20 to 30 years? Where are the directions?
Well, yeah, that's a very important question. And frankly, I think it means that we have to make use of what we have learned from the past 50 years to anticipate what we need to have as adequate tools for moving forward into the next quarter and half century. It's very clear from the tools that we now have, which are increasingly adequate to deal with the things that happen to pavements due to traffic and climatic effects. It's clear that we're going to have a much better understanding of mechanics. And by that, I mean not just elastic or elastoplastic, but actual plasticity theory and fracture and aging and healing. All of these things make much more use of thermodynamics than what we have had inadequate use in the times past. So the pavement engineer who's going to be involved in the very important essential role in managing pavement networks is going to have to understand mechanics and the ability to predict all of these types of distress, and also to understand the way to use non-destructive testing to give a much fuller, more accurate picture of what every single pavement section in a network, what its condition is and how quickly its condition is changing. That's going to be inadequate unless these things can cover the entire network frequently and can feed accurate information in to assist in making accurate predictions of the appearance and rate of appearance of all these different types of distress. And we'll have to make use of the understanding of viscoelasticity, even nonlinear viscoelasticity, the use of thermodynamics, rate processes, and things of that sort.
Yeah. Thank you.
These are the things that future pavement engineers need to study and to understand well enough to actually apply it practically. This is going to be a very expensive process, and it will be needlessly more expensive, but if we don't prepare to make intelligent use of all of these mechanics and their applications.
Yeah, thank you, Darlington. I think that's very important. Our last question would be, can you give some words to the young professionals regarding their career development? For example, how to design their career paths, how to do the good research, excellent research. What is your experience for the young professionals?
Yes, the young folks need to study the things that I've just mentioned as part of their academic preparation, but they also need to actually see what these things are. Dealing with a pavement in the abstract just does not work. You actually have to get out and look at these things and do some of the measurements yourself so you understand what they are. Having field experience and laboratory experience, so you know where the material properties come from, what they constitute, and that they're measured the right way and accurately and precisely. Plus all the academic preparation. All of these are things that will make it possible for a young professional in the future to be able to do all of the kinds of things that managing a very large infrastructure system will require. So frankly, when we started into pavements, trying to put together methods of predicting the pavements processes, we were using tools that were entirely inadequate. Pavements and the materials that they're made of and the processes that they are subject, the deterioration processes that they're subject to, are probably the most complicated structures that engineers have to deal with anywhere. And that has to be understood and recognized by everyone who goes into it. However, with a proper understanding and with the tools that we now have, we will be able to get on top of the deterioration process on a network level. It will be a very satisfying professional career, be able to do that, to have all the understanding that you need and the tools that it takes to make predictions and efficiently distribute the needed rehabilitation and maintenance funds over an entire network on a continuing basis. This business of managing pavement networks to reduce the costs to a manageable level is going to be a major challenge. It is in our case because we didn't have the tools to start with. Trying to get on top of it now, and it'll be quite a long time before we catch up with it.
Yeah.
Young professional of the future will be able to do a huge service to the people that he serves, preparing himself for these kinds of things.
Yeah, thank you so much, Dr. Lytton. We very appreciate your experience, your view to the pavement engineering. Actually, we get another lesson from you now. So thank you so much. Thank you for sharing your experience to the TRC 2021 conferences. That's the end of the interview. Thank you so much.
Transportation Research Congress, all success.
Okay, thank you, Dr. Lytton.